My first talk today is about the GW approximation for the electronic self-energy. The GW method is based on many-body perturbation theory. This approach can be used to calculate excitation energies. So in this sense, it is complementary to density functional theory, which is in practice limited to the ground state of many electron systems. The specs code is an implementation of the GW method. Over the years, we have added further functionalities. QSGW, which is a self-consistent version of GW, a combination of GW with spin-orbit coupling, a new self-energy that describes electron-magnon scattering, Hubbard U parameters, which will be the topic of my second talk, Wannier functions, also Wannier interpolation, hybrid functionals, RPA total energies, Bethe-Salpeter equation for excitons and magnons, and so on. As a motivation, I want to start with density functional theory, particularly with the Cohen-Sham formulation of density functional theory. This formulation maps the fully interacting many-electron system onto a non-interacting auxiliary many-electron system, the so-called Cohen-Sham system. Since it is non-interacting, we can write down the equation of motion for a single electron in this system, which is the Cohen-Sham equation. The Cohen-Sham equation consists of the kinetic energy, the external potential, the Hartree potential, which is the electrostatic potential created by all electrons in the system, and we have the exchange correlation potential. The exchange correlation potential is created in such a way that the total electronic density that we obtain from the iterative solution of the Cohen-Sham equation is identical to the exact total electronic density of the real interacting system in its ground state. We can say the electronic density is the one thing the Cohen-Sham system has in common with the real interacting system. Since we still have to resort to approximations for the exchange correlation functional, we will of course not obtain the exact electronic density in practice. The resulting total density of the real system can then be plugged into all kinds of density functionals to calculate ground state expectation values of the many-body system. For example, the total energy, atomic forces, magnetic moments, dipole moments, and so on. On the other hand, you have already performed band structure calculations with Fleur. And the band structure is a graphical representation of excited states. So what was that calculation? What you did was you plotted the Cohen-Sham eigenvalues as a function of the Bloch momentum k. This gives you a band structure. However, these eigenvalues are just Lagrangian multipliers. They are mathematical tools that allow you to utilize the variational principle of the ground state total energy. Strictly speaking, one cannot endow them with a physical meaning. On the other hand, experience tells us that this approach works quite well. We usually get a band structure that qualitatively agrees with experiment. However, quantitatively, they are discrepancies. This diagram shows the theoretical band gap of a variety of simple semiconductors and insulators as a function of the experimental band gap. An exact theory would give points only on this diagonal line. but LDA strongly underestimates the band gaps, sometimes by a factor of 2 or more. The GW method, on the other hand, yields band gaps much closer to this ideal line. We can say that we calculate in GW approximate excitation energies of a many-electron system described by the many-body Schrödinger equation. The central quantity in many-body perturbation theory is not the electronic density as in density functional theory. It is the single particle green function, which can be interpreted as a complex generalized density. It is a function that depends on 2 points in space, r and r', and it also depends on time. Here you see its mathematical definition. But instead of discussing the mathematical definition, I rather want to give you a physical interpretation of this quantity. The green function is the quantum mechanical probability amplitude for a propagation process of an additional particle. The particle can be an electron or a hole. It is injected into the many-body system at the point r' at time t', and it propagates to the point r at a later time t when it is removed from the system. The reason why we are interested in the green function becomes clear when we Fourier transform it. We go from the time domain to the frequency domain. The resulting frequency-dependent function contains in the denominators just those eigenvalues E that we have seen on the previous slide in the many-body Schrödinger equation. The excitation energies in the round brackets are what one measures in photoemission spectroscopy, where we either emit an electron, direct photoemission, or we inject an electron, inverse photoemission. This is why quantities of an n-1 particle system appear for direct photoemission and quantities of an n+1 particle system appear for inverse photoemission. To derive an equation for the green function, let us remember again that the green function is the probability amplitude for a propagation process. Such a quantum mechanical probability amplitude is given by the sum over all probability amplitudes of paths that the particle can possibly go to propagate from A to B. One such path is shown in the following. Let us assume an electron first goes from A to this point without undergoing any scattering process. The corresponding probability amplitude will be given by the green function of a non-interacting reference system. We call this green function G0. But then there might be a scattering event, electronic exchange in this case. The electron exchanges its role with an electron that happens to be here, and this second electron then continues the propagation. A bit later, there might be another scattering event, a screening of first order, and finally the electron reaches point B. As you see, the scattering events, electron exchange, screening, are drawn in the form of diagrams, so-called Feynman diagrams. Feynman diagrams are nothing else than high-dimensional mathematical integrals, expressed by physically intuitive pictures. To sum overall possible scattering paths, we make use of a quantity, the self-energy, that is defined as the sum over all such scattering diagrams. So it would contain electron exchange, electronic screening of all orders, excitonic effects, and so on. Then the shown scattering path would be contained in the expression G0, sigma, G0, sigma, G0. Of course, you can also have 3 scattering events, or 4, or only 1, or none at all. The green function of the interacting system, G, can then be written as an infinite series of terms. By factoring out the green function of the real system, G, on the right-hand side, we arrive at this concise equation, which is called the Dyson equation. The Dyson equation relates the green function of the real interacting system, G, to the green function of a non-interacting reference system, G0. G0 can be obtained from any mean field system, for example, Cohen-Sham density functional theory using functionals like LDA, PBE, or any other GGA, LDA plus U, hybrid functionals, or Hartree-Fock. To emphasize the starting point dependence, one sometimes sees notations like this: GW add LDA. In most GW codes, the Dyson equation is not solved directly. One instead employs a reformulation of the Dyson equation in the form of an effective single-particle equation of motion, the quasi-particle equation. This is an exact reformulation. Now we are back with something that looks familiar. We have the kinetic energy again, the external potential, and the Hartree potential. Up to this point, the equation looks like the Cohen-Sham equation. The last term, however, looks different. It contains the self-energy and describes the exchange and correlation processes. The self-energy is non-local and energy-dependent. It might appear curious that the eigenvalue that we want to determine appears also in the operator on the left-hand side as an argument to the self-energy. The quasi-particle equation is thus a nonlinear equation. The underlying reason for this is the fact that electronic screening is a dynamical effect. A fast electron is less efficiently screened than a slow electron. Since the self-energy is non-Hermitian, the eigenvalue will not be real in general, but complex. The two components give the excitation energy as the real part, and the excitation lifetime, or rather its reciprocal value, in the imaginary part. At this point, we have only defined the self-energy theoretically, but we do not have a working approximation for it yet. A popular approximation is the GW self-energy, which I want to motivate now. If you expand the self-energy in the bare Coulomb interaction, V, and only retain the linear term, you end up with the self-energy G0 times V. This is nothing else than the Hartree-Fock approximation. However, as we know, Hartree-Fock is a poor approach for extended electronic systems. A better approximation is obtained if we consider quasi-particles instead of the strongly interacting bare electrons. Imagine you place an electron into a many-electron system. This electron will repel all the other electrons in its neighborhood, and a Coulomb hole will form around it. The entity of the central electron together with its Coulomb hole is called a quasi-particle. As the effective charge of such a quasi-particle is smaller than that of an electron, the quasi-particle interaction W is smaller than the bare Coulomb interaction V. As a consequence, expanding the self-energy in terms of the screened interaction W will give a better approximation than Hartree-Fock. The linear term G0 times W is just the GW approximation. We can say that GW corresponds to the Hartree-Fock method with a dynamically screened Coulomb interaction. The corresponding potential becomes time-dependent. Let us now see how the screened interaction is calculated. A test charge at a point R will feel a screened potential W created by the charges of a quasi-particle. The central electron contributes with V, and the charge cloud around it contributes with this second term, where we integrate over the induced charge. The induced charge itself is induced by the Coulomb potential V of the central electron, and the charge is then obtained by integrating this perturbing potential V with the density response function P. But the induced charge gives rise to another perturbing potential, which in turn leads to a charge redistribution again. This is a feedback effect, which goes to arbitrary order. In this way, we get an infinite series for the screened interaction, which can again be written in a concise form, in the same way we did it with the Dyson equation before. Multiplying the infinite series with the green function gives an infinite series for the GW self-energy. Each term of it can be expressed as a Feynman diagram. This derivation, or rather motivation, of the GW approximation might sound a bit vague. Indeed, there is a firmer theoretical foundation. Actually, one can derive the GW equations in different ways. Here, I want to mention the Hedin equations. They are a set of integral differential equations of the green function, G, the self-energy, sigma, the screened interaction, W, the polarization function, P, and the vertex function, gamma. The self-consistent solution of this set of equations would give the exact solution of the many-body problem. The self-consistent cycle is often illustrated by this Hedin pentagon. Of course, an exact solution of the Hedin equations is impossible in practice. This should already be clear from the equation for the vertex function, which contains a 16-dimensional integral. However, if we start from Hartree theory for the reference system, the vertex function has a very simple form, and we can perform one iteration in the Hedin pentagon. As a result, we obtain the GW approximation for the self-energy. The polarization function is approximated by the product of two green functions. This is called random phase approximation and will play a role in my second talk today about the Hubbard-Yu parameters. Most implementations of the GW method exploit the formal similarity of the quasi-particle equation with the Kohn-Sham equation by writing the quasi-particle energies as a correction on the Kohn-Sham energies. Here we have used perturbation theory of first order with the difference of the self-energy and the exchange correlation potential as the perturbing operator. This is still a nonlinear equation. The quasi-particle energy also appears on the right-hand side. As a further simplification, one often Taylor expands the self-energy up to linear order, which can then be used to eliminate the energy dependence on the right-hand side. The prefactor, Z, is called the renormalization factor. It is between 0 and 1 and determines how much of the quasiparticle weight lies in the main quasiparticle peak. In the specs code, both solutions are given in the standard output. Specs can also solve the quasiparticle equation directly in a basis set, which goes beyond this perturbative ansatz. And it can also solve the Dyson equation. I will come back to this point at the end of the talk. In a GW code, two basis sets are needed. The first is the basis for the wave functions, for which one can employ all kinds of basis sets used in electronic structure calculations: Gaussians, plane waves, PAWs, LMTOs, and the LAPW basis set, which is used in our codes. The second basis is required for the representation of two particle quantities. For example, whenever an electron interacts with another, we have an incoming wave and a scattered outgoing wave. Together, they form a wave function product. The choice of the product basis should depend on the basis for the wave functions. For Gaussians, one would use an auxiliary Gaussian basis, which is used for density fitting in the DFT code. For plane waves, the choice is simple. The product of plane waves is a plane wave again. And for the LAPW method, we use the so-called mixed product basis, which I want to describe briefly in the following. To remind you, the LAPW basis is based on a partitioning of space into two regions: the Muffin-Tin spheres, which are centered at the atomic nuclei, and the remaining interstitial region. We use plane waves in the interstitial region with a cutoff Gmax for the momentum k plus g. And in the Muffin-Tin spheres, we employ products of radial functions and spherical harmonics with a cutoff Lmax for the L quantum number. Taking products of these functions will yield the mixed product basis. For plane waves, this is straightforward, as the product of plane waves is a plane wave again. Here we see a possible problem of practical calculations. Since the two exponents sum in the product, it seems that we have to take twice the cutoff radius Gmax, which would lead to very expensive calculations. A similar problem is seen for the Muffin-Tin spheres. The product of spherical harmonics of L quantum numbers L and L prime requires an expansion up to L plus L prime, and this pushes the L cutoff for the product functions to twice L max. Fortunately, it turns out that practical GW calculations show a favorable convergence behavior. We do not have to go to the exact limits. For silicon, we find that instead of twice Gmax, about 3/4 of Gmax gives sufficient accuracy. And a similarly fast convergence we observe for Lmax. The corresponding cutoff parameters can be defined in the specs input file using the keywords gcut and lcut. There are some more parameters to fine-tune the mixed product basis, all parameters are defined in the section M-basis. If you don't specify the parameters explicitly, specs will use default values or values optimized to the respective DFT data. In the GW implementation, we divide the GW self-energy into two parts, the exchange and the correlation part. This separation is made because the two terms have a different mathematical structure and different algorithms are used to evaluate them. As already mentioned, the exchange self-energy, G times V, corresponds to Hartree-Fock, and here we see it explicitly. The Coulomb interaction acts instantaneously, so the time arguments are effectively identical, and for identical time arguments, the green function is just the density matrix, which, together with the Coulomb potential, yields the Hartree-Fock exchange potential. The correlation part of the self-energy is much more expensive to evaluate because it is a dynamical quantity and requires a convolution in the frequency domain from -infinity to +infinity. Two techniques are implemented in specs to compute this convolution. Both employ the imaginary frequency axis because the pole structure of the quantities is such that on the imaginary axis we are far away from the poles and the quantities show a smooth behavior. The first technique is analytic continuation, where the self-energy is fully evaluated on the imaginary axis and then analytically continued to the real frequency axis. This technique is easy to implement, easy to use, and allows for fast computations. However, the last step, the analytic continuation, is a critical and sometimes ill-defined step. Therefore, there is a more accurate technique called contour deformation, where instead of integrating from -infinity to +infinity, we integrate along this deformed contour. The integration contour is chosen in such a way that the integrated value is identical to what you would get if you did the integration along the real frequency axis. Contour deformation is more accurate than analytic continuation, but it also needs more parameters and is computationally more expensive. The corresponding keywords in the specs input file are continue and contour. Continue is the default. Let us have a look at the first example, bulk silicon. This is the LDA band structure. A comparison with experimental band gaps shows a strong underestimation both for the direct band gap and also for the indirect band gap. The GW calculation yields the blue band structure. The filled bands shift down, the empty bands shift up. Now, to compare with experiment, we align the valence band maximum. We find the GW band gaps, both direct and indirect, to be quite close to experiment. Silicon was the first material to which realistic GW calculations were applied to, independently by Hybertson and Louis and by Godby, Schlüter and Sham. The GW value still slightly underestimates experiment, which might be due to the starting point dependence of GW. This dependence can be overcome by a self-consistent GW scheme, for example, the so-called quasi-particle self-consistent GW, QSGW, which was proposed by Faleev, van Schilfgaarde and Kotani. QSGW can be understood as an iterative solution of Hedin's equations, but leaving out the complicated vertex function gamma. This causes some inconsistency in the theory, and as a result, the bandgap values of silicon now overshoot. On the other hand, they are materials where QSGW is clearly more successful than one-shot GW. GW calculations are notoriously difficult to converge, in particular with respect to the number of bands. A well-known example for this problem is zinc oxide. Over many years, the GW bandgaps showed quite a large scatter of values, but all underestimated quite strongly the experimental value of 3.4 eV. Then, in 2010, Shi and co-workers published a GW bandgap that agreed perfectly with experiment. In the paper, they explained the difference in values by the very slow band convergence in this material. We did our own calculation in 2011 and obtained a smaller value, 2.83 eV. Nowadays, everybody agrees on a value around 2.8 eV. However, we could confirm the main result of Shi and co-workers, namely the very slow band convergence in zinc oxide. We had to include 3000 bands and the bandgap was still not fully converged. This also puts very high demands on the quality of the basis set, because it has to represent accurate eigenstates over a very large energy range. As a comparison, for a normal DFT calculation, we only need the few occupied bands that, on this energy scale, fit all in the thin red line. There are not so many GW codes that can treat metallic systems. What are the extra challenges in the case of a metal? Let us consider the polarization function, which can be written as a sum over virtual excitations that go from occupied states, n, into unoccupied states, n'. For a bandgap material, the separation of occupied states and unoccupied states is clear, and it is straightforward to sum over the virtual excitations. On the other hand, if the Fermi surface cuts the electronic bands, one and the same band can be partly occupied and partly unoccupied. This requires the Fermi surface to be sampled accurately in reciprocal space. We use the tetrahedron method for this purpose. However, there is an extra contribution that originates from infinitesimal virtual transitions from slightly below the Fermi surface to slightly above. This contribution is not captured by the tetrahedron method. Luckily, one can derive an analytic formula for it, the Drude term. It depends on the plasma frequency, which can be calculated by an integration over the Fermi surface. The Drude term is crucially important for the GW band structure of metals, because it cancels an unphysical anomaly that we find in the metallic Hartree-Fock bands. These bands show a strange behavior at the Fermi energy. Closer inspection shows that the band gradient exhibits a logarithmic divergence just where the band crosses the Fermi surface. GW contains Hartree-Fock, but by virtue of the Drude term, the logarithmic divergence is exactly cancelled in the GW bands. As a result, the GW bands are free of any anomalous behavior at the Fermi energy. We can also observe that the GW bandwidth is slightly smaller than in Kohn-Sham DFT. This is because the quasiparticles have an increased effective mass due to the additional polarization cloud. About 10 years ago, we combined the GW approximation with spin-orbit coupling, which is of importance for the treatment of heavy elements. The spin-orbit coupling makes it possible that a propagating electron can spontaneously flip its spin, which leads to off-diagonal elements of the Green function in spin space. Likewise, the self-energy acquires off-diagonal elements which lead to a many-body renormalization of the spin-orbit coupling itself. As an example, we consider mercury telluride. Mercury telluride exhibits an inverted band gap at the gamma point. The valence band acquires the orbital character of the conduction band and vice versa. In such a situation, one defines the band gap with a negative sign. Another important parameter in this band structure is the spin-orbit splitting. Theoretical values of these parameters are compiled in the table together with experimental measurements. LDA gives the correct signs, negative for the band gap, positive for the splitting, but the absolute values disagree with experiment. In particular, LDA gives the wrong ordering of states at the gamma point. This wrong ordering is corrected by the one-shot GW approach. In the first case, the spin-orbit coupling is included as a simple a posteriori correction. In the second, it is incorporated into the GW approximation in a consistent way. And only then do we obtain a correction of the spin-orbit splitting as well. If we run the whole calculation self-consistently in a QSGW approach, we get the best agreement with experiment. With the last example, we return to silicon. In this example, we present direct solutions of the Dyson equation, which will give access to satellite features. The resulting spectral function can be understood as a vertical cut through the band structure. It contains the energetic location of the quasiparticle state and its lifetime broadening. The lifetime broadening grows with the distance from the Fermi energy. This is because the higher the energy, the more scattering channels are open for the particle to scatter, which reduces its lifetime and increases the lifetime broadening. Let us now extend the energy range to larger binding energies. Surprisingly, additional intensity is seen in the GW spectral function in a region where no bands exist. The origin of this intensity can be understood if we remind ourselves of the process in photoemission spectroscopy. The sample is exposed to a beam of light. When a photon hits an electron, it can transfer its energy to it, and the electron is emitted from the material. The kinetic energy of the emitted electron is measured in the detector. It is directly related to the electron's binding energy in the material. However, it can also happen that only part of the photon energy is transferred to the electron and the rest excites a plasmon in the sample. The emitted electron then has a lower kinetic energy, so it seems to have come from a higher binding energy which causes the signal here. In this sense, it is a many-body phenomenon that is clearly outside the scope of DFT. To some extent, the intensity looks like a fuzzy image of the quasiparticle bands shifted in energy. The energy shift corresponds to the energy of the plasmon excited in the process. You will perform such a calculation this afternoon in the hands-on session. Finally, I would like to say a few words about practical calculations with the SPEX code. Any calculation has to start with a self-consistent DFT run, which gives the non-interacting reference system. We use the FLIR code for this step. SPEX needs the Korn-Sham eigensolutions on a special k-point set. This k-point set should form a group under vector addition. If k and k' are in the set, their sum k plus k' should also be an element of the set. We run SPEX to create this special mesh. Then we need to run FLIR again to generate the eigensolutions on this new k-point set. Finally, we can run SPEX, for example, for a one-shot GW calculation. The job definition, shown here, requests the calculation of quasi-particle energies for the first, second, third, fourth, and sixth state at the x point. The last three steps can be combined into a single SPEX run if we simply specify the keyword iterate in the SPEX input file. This is, of course, more convenient, and we will use this feature in the hands-on session, but it is also less general. For example, hybrid functionals or the QSGW method require the other procedure. The calculation of GW band structures is less straightforward than in DFT, because due to the special form of the k-point set, we cannot add arbitrary q-points to it. However, we can add a single arbitrary q-point provided that we also include all shifted k-points. Then, for each new q-point, we would have to run in this order SPEX, FLIR, and again SPEX. To simplify the procedure, there is a shell script, SPEX band, that runs SPEX and FLIR automatically for the whole list of q-points. A simpler approach to calculate GW band structures is with Wanyi interpolation. The Wanyi functions are defined in a section Wanyi in the SPEX input file. In this case, we use maximally localized Wanyi functions of sp3 hybrid orbitals. Compilation and installation of the SPEX code is done in 3 steps. First, configuration. The configure script accepts a number of options that let you customize your compilation. For example, the option with 1 links SPEX to the Wanyi90 library. You can also request an MPI parallelized version at this point. Second, compilation. This is done with the make command. And third, installation with make install. I summarize. Excitation energies and lifetimes of the n+1 and n-1 electron system can be readily obtained from the one-particle green function. These excitation energies form the band structure in solids. The green function obeys an integral Dyson equation, which may be rewritten as a quasi-particle equation with a self-energy as a scattering potential that takes into account all exchange and correlation effects beyond the Hartree potential. The GW approximation constitutes the expansion of the self-energy up to linear order in the screened interaction W. It is usually implemented as a perturbative correction on a DFT band structure, but a self-consistent solution, QSGW, is possible too.